Hi everyone, today we'll be exploring the groundbreaking paper, Attention is All You Need, which introduced the transformer model. This paper has had a massive impact on the field of machine learning, particularly in natural language processing and computer vision.
That's right. Transformers have become foundational in the AI world, especially with the development of models like BERT and GPT-3. But did you know they've also made their way into image recognition and even multimodal learning?
Absolutely. To summarize the recent top uses. First, transformers have revolutionized natural language processing, NLP. They've empowered models to handle tasks like summarization, translation, and sentiment analysis far more efficiently than older RN-based systems. Second, we've got vision transformers, or VIT, in computer vision, which handle images by breaking them into patches, effectively challenging the dominance of convolutional neural networks, CNNs. And third, there's multimodal learning, where transformers combine text and images to create impressive applications, like image captioning and creative AI models, broadening the horizons of how AI can work across different types of data.
It's amazing how one architecture can do all that. But I guess we should get into the transcript now to understand how it all works.
Right. The transcript is based on a discussion of the Attention is All You Need paper. We'll guide you through the sections starting with the abstract, which outlines the transformer's goal. A model for sequence tasks that does away with recurrence and convolution, using only attention. As we move along, we'll dive into the introduction, background, and details of the model architecture, making it easy to follow even if you're new to these concepts.
So it's kind of like a crash course on transformers, but broken down into a friendly chat?
Exactly. Throughout the transcript, you'll see a conversation where I explain the core ideas, and you'll ask questions similar to what our listeners might be wondering about. We'll cover the key innovations like multi-head attention, encoder-decoder stacks, and positional encoding, and discuss why transformers made such a leap forward compared to older models.
Got it. And for everyone listening, feel free to follow along as we discuss how each part of the architecture contributes to making the transformer one of the most important AI models out there.
Perfect. All right, let's get started with the abstract and set the stage for why attention really is all you need in sequence modeling. Today we're going to dive into the abstract of an important paper in neural networks, titled, Attention is All You Need. This paper introduces the transformer architecture, a model designed for sequence transduction tasks like language translation. It essentially replaces the older RNN and CNN-based models. Instead of using RNNs or CNNs along with attention mechanisms, the transformer relies solely on attention, completely eliminating recurrence and convolution. This shift allows for parallelization, which makes training faster and more efficient.
Wait, so they got rid of RNNs and CNNs altogether? How does that even work?
Exactly. Instead of using the RNN's sequential processing, the transformer uses attention to connect every input and output position at the same time. This makes the training process much more efficient. The model also uses positional encodings to keep track of the sequence order, even though it doesn't rely on recurrence.
Oh, I see. Does that make tasks like translation better?
Yes, absolutely. For tasks like translating English to German, the transformer outperformed previous models, achieving a BLEU score of 28.4, and it trained faster too. By removing those sequential dependencies, the model becomes more efficient, and using multi-head attention helps it understand context better by focusing on multiple aspects at once.
So, is multi-head attention kind of like having multiple viewpoints?
Exactly right. It allows the model to examine the sequence from different perspectives, which helps it understand complex relationships like the syntax and meaning more deeply.
Got it. So, what's the big takeaway here?
The main takeaway is that the transformer moves away from relying on recurrence and convolution, and instead uses attention to achieve better performance and efficiency. Basically, it shows that attention is all you need for sequence tasks, and it's opened the door to even more powerful language models. All right, let's talk about the introduction of the paper, which explains why the transformer was created. Previous models like RNNs, LSTMs, and GRUs were quite powerful for tasks like translation, but they had some serious limitations. They processed sequences one element at a time, which created a bottleneck, especially for longer sequences.
Processing one word at a time must take forever for large texts.
Exactly. This sequential nature really slowed down training and made parallelization almost impossible. There were some recent attempts to fix this, like using factorization or conditional computation, but none of these approaches fully solved the bottleneck.
So, they tried a lot of fixes, but nothing worked well enough?
That's right, and that's where attention mechanisms came in. Unlike RNNs, attention allows the model to focus on all parts of the input simultaneously. This meant the transformer could look at the entire sequence at once, without relying on recurrence.
Wasn't dropping RNNs a bit risky?
Yes, it definitely was a bold move. RNNs were the state of the art at the time, but they weren't practical at scale. The authors showed that attention alone could efficiently manage dependencies. They also compared their model with convolution-based models like ByteNet. While convolutions improved efficiency, they still needed a lot of layers to link distant elements, whereas attention could directly connect all elements at once.
So, attention made those connections more direct?
Exactly. It reduced the complexity by directly connecting distant parts of the sequence, which was especially important for understanding long-range dependencies, like translating more complex sentences.
But how did they deal with word order?
Good question. They used positional encodings to indicate where each word was in the sequence. This gave the model a sense of order, despite not having recurrence. The introduction wraps up by stating that the transformer achieved state-of-the-art results, and it did so with much faster training, setting a new benchmark in sequence modeling and overcoming the limitations of older methods.
It sounds like they really rethought the problem and found an elegant solution.
Absolutely. By focusing on attention, they managed to break through the limitations of previous models, marking a major step forward in natural language processing. Let's go over the background section, which explains why the limitations of older models led to the development of the transformer. Traditional models like RNNs processed sequences in a step-by-step manner, which caused major bottlenecks. Convolutional models like ByteNet helped by improving parallelization, but they still struggled with capturing long-range dependencies since the number of operations increased with the distance between elements.
So, convolutional models were faster, but they still weren't great for handling long sequences?
Exactly right. That's where self-attention comes into play. Self-attention directly connects every position in a sequence, no matter how far apart they are, which makes computation more efficient.
That definitely sounds a lot more straightforward.
It is. Self-attention had been used before for tasks like summarization, but the real breakthrough with the transformer was making it the core of the architecture, completely replacing RNs and convolutions. The key innovation here was multi-head attention. By using multiple heads, the model could focus on different aspects of the data at the same time, which greatly enhanced its understanding.
So, it's like having multiple viewpoints analyzing the same data?
Exactly. This approach allows the model to capture more complex relationships. Another benefit is that the computational complexity of self-attention is actually lower compared to RNNs, which makes it faster, especially for longer sequences.
So, they figured out a way to achieve more with fewer steps?
Precisely. Self-attention enables every element in the sequence to connect directly with every other element, making it much easier to learn long-range dependencies. The transformer essentially eliminated the bottlenecks associated with RNs and convolutions by rethinking the whole approach to processing sequences. In summary, the transformer's use of self-attention addressed the core limitations of previous models, providing a far more efficient way to process sequences and understand relationships between elements. Let's dive into the model architecture of the transformer. It follows an encoder-decoder structure, where the encoder processes the input sequence and the decoder generates the output. The real innovation here is how these parts function internally using attention.
So, it's still an encoder-decoder setup like the traditional models, but it works differently?
Exactly. Instead of relying on RNNs or convolutional layers like older models, the transformer builds on layers of self-attention and fully connected networks. The encoder consists of 6 identical layers, and each of these layers has 2 sub-layers: a multi-head self-attention mechanism and a fully connected feed-forward network.
Why do they repeat those layers?
Repeating these layers allows each one to progressively refine the representation of the input. This way, the model captures increasingly complex features, such as the grammar, context, and relationships within the sequence.
That makes sense. Does the decoder work in a similar way?
Yes, it does. The decoder also has 6 identical layers, but with one extra component, an encoder-decoder attention sublayer. This allows the decoder to focus on the relevant parts of the encoded input while generating each part of the output.
How does the decoder decide what to focus on?
That's where multi-head attention comes into play. It allows the model to consider different aspects of the sequence simultaneously. In the transformer, there are 8 attention heads, meaning it can understand various nuances and contexts for each word.
That's pretty clever. But doesn't using multiple heads make the model computationally heavy?
Surprisingly, it's not as heavy as you might think. Each head works on a smaller subspace of the input, so the overall computational cost is similar to that of using a single head. The outputs from all the heads are then combined, which gives the model a more comprehensive understanding without a huge computational burden.
Got it. And what about the fully connected network? How does that fit into all this?
After the attention mechanisms do their work, the fully connected network takes the output and applies more complex transformations to further refine it. This part of the architecture involves 2 linear layers with a ReLU activation function in between.
And this entire process repeats 6 times, right? That's how the model builds complexity?
Exactly. On top of that, the model uses residual connections, which help ensure that information flows smoothly through all the layers, preventing problems like vanishing gradients.
So the residual connections are like shortcuts to keep the important information intact. That's really useful, especially in deep architectures.
Absolutely. Residuals help the model maintain crucial features across layers. Another important aspect is positional encoding. Since the transformer doesn't have a built-in way to understand sequence order like RNNs do, positional encodings are added. They use sine and cosine functions to convey each token's position within the sequence.
So the positional encodings act like a kind of memory, helping the model keep track of the order?
Exactly right. Positional encodings preserve the sequence information while also allowing the transformer to take full advantage of parallel processing, a key feature that makes it so powerful. To sum it up, the transformer uses layers of encoders and decoders with multi-head self-attention and feed-forward networks. This setup enables it to efficiently capture relationships across sequences, while also taking advantage of parallel processing.
Now I see why the transformer was such a big deal. Every part of the design seems to address the limitations of earlier models.
Right on. The entire architecture was reimagined to create something leaner, faster, and more capable. It really is a fascinating leap forward in sequence modeling, isn't it? Let's take a closer look at the encoder and decoder stacks. Both of these are made up of multiple identical layers, each serving a specific function. Let's start with the encoder.
Sure. So, what exactly does each of those 6 identical layers do?
Each encoder layer has 2 main sublayers, a multi-head self-attention mechanism and a feed-forward network. The multi-head self-attention allows each word in the sequence to focus on every other word, which helps the model understand context, like which words are related to each other. Having multiple heads means the model can understand different aspects, grammar, meaning, and relationships simultaneously.
That's pretty cool. And what happens after that with the feed-forward network?
The feed-forward network takes the information from the attention mechanism and further processes it. It's essentially a 2-layer network with a ReLU activation function in between, which helps enrich the data representation. Each of these sublayers also includes residual connections, which serve as shortcuts. These ensure that no important information gets lost as it moves through all 6 layers.
So, residual connections are there to make sure nothing crucial gets lost. That must really help keep the data moving smoothly through the layers.
Exactly. These residual connections, combined with layer normalization, help stabilize the input to each layer and ensure that learning remains consistent throughout the model.
And what about the decoder? Is it built the same way?
The decoder is quite similar but has an extra sublayer called encoder-decoder attention. This additional sublayer allows the decoder to refer back to the encoded input while generating each word of the output. This way, the decoder ensures that every word it generates is appropriately related to the original input. Plus, the decoder's self-attention has a special feature called masking, which means it can only focus on positions that have already been generated, preventing it from looking ahead and effectively cheating during generation.
So, the decoder is referencing the input while it generates each word, and the masking makes sure it doesn't look ahead?
Exactly. This setup makes sure that each word is generated based on the context provided up to that point, without peeking ahead. The combination of multi-head attention, feed-forward networks, residual connections, and masking provides a very powerful framework for processing and generating sequences effectively. To summarize, the encoder constructs a detailed, comprehensive representation of the input, while the decoder uses that understanding to generate output step by step, ensuring that the output remains coherent and contextually accurate. This balance between comprehension and generation is what makes the transformer so powerful.
It's amazing how everything comes together, like two halves of a brain, one for understanding and the other for speaking.
Precisely. It's that beautiful balance between understanding and generation that has revolutionized the way we model sequences. All right, let's get into attention, which is a key part of the transformer, hence the name, attention is all you need. Basically, attention allows the model to selectively focus on different parts of an input sequence, much like how we naturally focus on the important words in a sentence.
So, it helps the model figure out which words matter the most.
Exactly. The main idea here is called scaled dot product attention. It works by calculating a score between words using the dot product of their vector representations, what we call queries and keys. High scores mean there's a strong relationship between the words. Then, we scale those scores by dividing by the square root of the vector dimensions. This keeps the values stable, making them easier to work with when we apply the softmax function.
What does the softmax do in this context?
Softmax turns these scores into weights that add up to 1, which helps determine how important each word is relative to the others. These weights are then applied to another set of vectors called values, which ultimately creates a new representation, highlighting important parts, like fluffy when we're talking about a cat.
And multi-head means that it looks at the data from multiple perspectives?
Exactly. With multi-head attention, there are multiple sets of these projections, each one, or head, focusing on a different aspect of the data, like grammar or meaning. Then, all these different outputs are combined, which gives a much richer representation, kind of like having multiple experts analyze a text from different angles.
So, in the end, the model gets a more thorough understanding of what's going on.
Yes, exactly. It's like getting different expert opinions to really understand the details. The transformer actually uses 3 kinds of attention: encoder self-attention, decoder self-attention, and encoder-decoder attention. With encoder self-attention asterisk, each word in the input sequence pays attention to every other word, which helps build a detailed, context-rich representation.
So each word ends up understanding its relationship to the others?
Right, and that's key for figuring out the correct meaning in context. Then, in decoder self-attention, each word focuses only on the words that came before it, thanks to masking. This ensures that the output is generated step by step without looking ahead.
So that means the model can't peek at future words while generating, right?
Exactly. Lastly, there's encoder-decoder attention. Here, the decoder looks at the output of the encoder while generating the final output. It's a bit like a translator who constantly refers back to the original source text to make sure everything is accurate.
So that means the output stays contextually accurate and consistent?
Precisely. This setup allows the transformer to capture long-range dependencies really well, which was a big challenge for older models. By focusing on just the right parts, the transformer keeps every word it generates relevant and context-aware. To wrap it up, the time-detention times mechanism is really the core of the transformer. It lets the model focus dynamically on the important parts of a sequence, build a strong context, and handle complex tasks like translation efficiently.
I get it now. Attention really is all you need to make those connections accurately and efficiently.
Absolutely. By simplifying things down to attention, the transformer solves a lot of the issues that older models faced, which is why it's become such a cornerstone in modern natural language processing. All right, let's break down position-wise feed-forward networks, embeddings and softmax, and positional encoding. Each of these plays a really important role in the transformer, starting with position-wise feed-forward networks asterisk. Each layer in the encoder and decoder has a feed-forward network that works on each word independently. It's made up of two linear transformations with a ReLU activation in between, which helps refine the data and capture more complex relationships before moving on to the next layer.
So, the same transformation is applied to every word?
Exactly. This uniform approach makes sure each word is processed consistently, which helps keep everything efficient and ensures that all words are enhanced in the same way. Now on to asterisk embeddings and softmax asterisk. Words are represented as vectors through times embeddings asterisk, which helps the model understand the relationships between them. The neat thing is that these embeddings are shared between the input and output sides, making the training process more efficient. Then there's the times softmax function, which turns the model's output into a probability distribution over the vocabulary to decide which word comes next.
So, embeddings help the model understand relationships between words, and softmax helps it pick the right words to generate?
Exactly. Embeddings are like the model's way of understanding the words, and softmax helps it actually produce understandable and coherent sentences. Lastly, there's asterisk positional encoding asterisk. Since the transformer doesn't naturally know the order of words, like RNNs do, times positional encodings are added to the word embeddings. These encodings use sine and cosine functions to give each word a unique position in the sequence, which helps the model understand the order and relative distance between words.
So, positional encoding kind of gives each word an address to indicate its position?
Yes, exactly. It tells the model where each word fits in the sequence, ensuring that the self-attention mechanism captures not only the meaning of each word, but also its place in the sentence. To sum it up, feed-forward networks refine the data, times embeddings and softmax help manage the input and generate the output, and times positional encoding times ensures the model understands the order of the words. Together, these components make the transformer really effective at understanding and generating language.
It makes sense now. All these parts working together are what make the transformer so powerful.
Absolutely. Each component tackles a specific challenge in sequence modeling, and together they create a highly efficient and capable model. Let's talk about why the authors chose self-attention for the transformer. Unlike RNNs, which go through sequences step by step, self-attention allows each word in a sequence to consider all the other words at the same time. This gives the model direct access to relevant information without needing to go through the entire sequence one by one.
Other than speed, are there any other advantages?
Absolutely. One big advantage is computational complexity. RNNs have to process everything sequentially, which can be really slow, especially with long sequences. Self-attention, on the other hand, works in parallel, so it can handle both short and long sequences much more efficiently.
So it scales better when things get bigger?
Exactly. It's kind of like being able to look at every page of a book at once, instead of reading page by page. Self-attention also reduces what's called path length, which means that every word can directly connect with any other word in the sequence. In RNNs, the information has to pass through multiple steps, which makes it tough to learn long-range dependencies.
So it makes sure the important context stays intact, no matter how far apart the words are.
Right. And while convolutional networks can handle things in parallel too, they still need multiple layers to connect words that are far apart. Self-attention manages to do this in just one layer, which makes everything simpler and more efficient.
Yeah, self-attention sounds a lot more straightforward than convolutions.
It really is. Plus, it adds interpretability. With self-attention, you can actually visualize which parts of the input the model is focusing on, so you get a better understanding of how it's making its decisions.
That sounds really useful for figuring out what's going on inside the model.
Absolutely. To sum it up, self-attention reduces complexity, allows for parallel processing, shortens the distance between important pieces of information, and makes the model easier to interpret. It's a much better approach for dealing with the complexities of language.
It feels like self-attention just solves all the problems that older models had.
Exactly. By focusing on self-attention, the authors came up with an elegant and powerful solution. That's a big part of why the transformer has become so influential in the world of natural language processing. All right, let's talk about how the transformer actually learns during the training phase. This is where the model moves from just being a bunch of formulas to actually generating meaningful text. The key parts of training are data and batching, hardware, optimizer, and regularization.
What kind of data did they use? And how did they get it ready?
They used data from the WMT 2014 dataset for English to German translations, which had about 4.5 million sentence pairs. For English to French, they used a larger dataset with 36 million pairs. To make training more efficient, they grouped sentences of similar lengths into batches. This way, the model doesn't waste too much time dealing with padding for shorter sentences.
Got it. What kind of hardware did they use for training?
They trained the model on 8 NVIDIA P100 GPUs. The base version of the model took around 12 hours for 100,000 steps, while the bigger version took about 3.5 days for 300,000 steps. Using multiple GPUs helped speed things up significantly.
And what did they use for optimizing the training?
They used something called the Atom Optimizer, which is a popular method for training models like this. They also used a special learning rate schedule, where the learning starts off fast and then gradually slows down after the first few thousand steps. This helps the model learn quickly at the beginning, but then allows for more precise adjustments later on.
That makes sense. Kind of like learning something new quickly at first, and then fine-tuning it slowly. Like learning a musical instrument.
Exactly. That's a great analogy. It helps avoid getting stuck in less effective ways of doing things. They also used regularization techniques, such as dropout, where 10% of the connections are temporarily dropped during training to prevent the model from relying too heavily on any one part. Another technique they used was label smoothing, which keeps the model a bit flexible and helps it stay open-minded instead of becoming overly confident in its predictions.
So, dropout and label smoothing are there to make sure the model learns properly and doesn't get too overconfident?
Precisely. Dropout makes sure that no single part of the model gets too dominant, and label smoothing helps avoid overconfidence. Both are really important for ensuring the model can generalize well to new data. To sum it up, they trained with large datasets and used efficient PIMS batching times and powerful hardware to speed things up. The Atom Optimizer asterisk, along with the times learning rate schedule asterisk, helped guide the learning process. And times dropout times an asterisk label smoothing times kept everything balanced and prevented overfitting. All of this together made the transformer both powerful and flexible.
It's impressive how much thought goes into the training process. Every piece seems to work together to help the transformer reach its best potential.
Absolutely. The success of the transformer isn't just about its architecture, it's also about the careful design of the training process. That combination is what makes it such a groundbreaking model in natural language processing. All right, let's dive into the results section and see how well the transformer actually performs. The authors tested it on 2 major translation tasks: English to German and English to French. And the results were pretty impressive. They used something called the DIMES BLEU score times to measure how good the translations were. And the transformer really stood out. For asterisk English to German asterisk, it got a asterisk 28.4 asterisk BLEU score, which was more than 2 points higher than what previous models had achieved. A big improvement in machine translation. And for asterisk English to French asterisk, it hit asterisk 41.8 times Cs, setting new records while also using less computational power compared to the older models.
So it was not only better but also more efficient?
Exactly. The transformer's design allowed it to process things in parallel, which cut down training time while still boosting performance. Even the base version of the model was better than the older ones, and it did all of this while using less computational power. They didn't just test it on translation, though. They also used the transformer for English constituency parsing asterisk, and it either matched or outperformed the specialized models that were designed just for that task. This really showed how versatile the transformer could be.
So it can do more than just translation?
Exactly. The transformer was built as a general sequence processing model, meaning it could handle all kinds of tasks beyond translation and do them really well. They also experimented with different versions of the model, like changing the number of layers and asterisk attention heads. They found that adding more heads generally helped performance up to a point, but after a certain number it didn't make much of a difference anymore. They also tweaked the dimensions of hidden layers and the feed-forward networks, which helped the model capture more complex patterns and improve the BLEU scores.
So they had to find the right balance with all these adjustments?
Exactly. It was all about finding the optimal setup. Tweaking things like dropout rates and the size of hidden layers was crucial for making sure the model didn't overfit and could generalize well to new data. To sum it all up, the transformer set new records for translation quality, and it did it more efficiently. Plus, it was flexible enough to handle a range of language tasks, not just translation. Its success came down to the clever architecture and the careful fine-tuning of every part, making it a huge step forward in natural language processing.
It sounds like they really nailed the balance between simplicity and power.
Absolutely. By rethinking how to process sequences with self-attention, they created something that was not only powerful, but also flexible and efficient. That's why the transformer has become the backbone of so much modern AI technology today. All right, let's wrap it up by talking about the conclusion. This is where the authors reflect on what they accomplished, why it matters, and where things could go next. Essentially, they're tying everything together: what worked, why it's important, and what might come in the future. The main takeaway is that the times transformer times represents a major shift in how we handle sequence tasks like translation. Instead of relying on complicated RNs and convolutions, the transformer relies entirely on asterisk attention asterisk, making the whole process simpler and more efficient.
So they're basically saying that the transformer proves you don't need those older, more complicated methods to get the best results.
Exactly. They really emphasize that attention is all you need. By removing the need for recurrence and convolution, they came up with a model that not only trained faster but also understood word relationships better. Their results on translation tasks showed that this attention-only approach could handle a wide range of sequence tasks effectively. They also talk about how scalable and versatile times the transformer is. It's not just good for translation, it's also great for other tasks like times constituency parsing asterisk, which shows it can be applied to various NLP challenges and even beyond.
So the transformer is more like a flexible tool that can adapt to different needs?
Exactly right. The transformer is kind of like a framework, a very adaptable one. Its use of modular attention mechanisms makes it useful for so many tasks, like translation, summarization, question answering, and even things beyond language, like image and audio processing. They also hint at asterisk future directions asterisk, like using the transformer for other types of data text, images, audio, even video. And that vision has pretty much come true now, with transformer-based models being used in all these different fields.
So they were already thinking about applying this beyond just text back then?
Absolutely. The transformer laid the groundwork for models like GPT, BERT, and even vision transformers, VIT. By putting attention at the core, they built a foundation that could handle a lot more than just text. The authors end on a pretty optimistic note, hoping their work would inspire further research, and they were definitely right. The transformer has led to countless innovations and has really transformed the field of AI across multiple domains.
It's pretty incredible how one paper can have such a huge impact across so many areas of AI.
Exactly. Some of the best breakthroughs come from rethinking old assumptions and finding simpler solutions. The transformer did just that. It redefined how we approach sequence modeling, and it's influenced pretty much all modern work in ELP. So to sum it up, the transformer got rid of recurrence and convolution, and instead used an attention-based approach, which made it faster, more efficient, and super adaptable across different tasks. This simple shift inspired a wave of new innovations.
That's really inspiring. It shows that even in a complex field like AI, there's always room for a new way of thinking.
Absolutely. The transformer was a big leap forward, and it's a great reminder that rethinking a problem can lead to truly groundbreaking advancements. Well, that about wraps up our discussion on the transformer today. It's truly fascinating how a single shift towards attention mechanisms has reshaped so many fields, from language to vision, and even beyond. Looking ahead, we can expect even more from this architecture. Maybe deeper integration across different types of data, or new ways for AI to understand and generate even more complex relationships.
Yeah, it feels like we're just scratching the surface. I mean, with models like GPT-4 and multimodal AI becoming more common, who knows what we'll be seeing in just a few years?
Exactly, the potential is enormous. The future of AI is all about creating systems that are more adaptable, more intuitive, and more capable of handling real-world complexity. And it's exciting to think that what we discussed today is laying the foundation for that future.
Absolutely. Thanks to everyone for joining us in this deep dive into the transformer.
Yes, thanks so much for listening. We hope you found it as fascinating as we did. Stay curious, and we'll see you next time for another journey into the world of AI.
Bye for now.